Um, Thank you for the introduction. So, good morning, everyone. So today we propose SpecTrans. It's a new sensing technology for surface classification. So it can classify transparent and highly specular surfaces, such as glass and transparent plastics. So with SpecTrans technology, we can build a wide set of applications in the real world. So we can create new museum experience or new user interface for floating displays. You can also enhance smartphones and enhance desktop computing. And you can also add a physical layer of information to a tablet device. So there has been a lot of interest in associating digital content with the physical world. For example, using printed text and numbers or through 2D barcodes. However, these are apparently obtrusive technology. So to avoid visual markers, we can also print barcodes and other fiduciary markers with invisible inks. So then only the computer system can see the markers. And in this case, they used IR inks. However, this adds extra cost and process. Also, people cannot know where the information is embedded. You can also use more complex technologies. For example, NFC tags and iBeacon are being used widely today. However, it is more physically complex instrumentation, and it adds additional costs. All right, so how can we identify surfaces without using tags or electronics? The most common technique is image-based classification. So we can classify the surface materials from textures. However, this technique only works for surfaces with distinct textures. Harrison and Harrison use a multi-spectral illumination and sensing with LEDs in 5 different wavelengths and light sensors for classify objects, surfaces. And this technique is single-directional lighting. And in general, this technique is limited to colored materials and does not work for transparent materials. And Magic Fingers uses a tiny video camera attached to the fingertip. And the technique used here is basically the same as conventional image classification. So it requires distinct texture patterns or micro-printed letters or 2D barcodes for surface recognition. So if they are completely flat or transparent surfaces, so Magic Finger cannot classify those surfaces. Actually, there's a wide variety of approaches for classifying the surfaces or user or device activities, and also embedding markers and tags to the physical world. So we discussed them in our paper, but we are not going to cover all of them in this talk. All right, so here's the problem. So the real world is very complex. So our living space consists of very wide variety of materials, and glass walls and shiny facades and metallic furnitures. In this talk, so we are interested in also supporting these textureless and highly specular and exotic materials. A shopping window should preserve a clear view of the object, and it is undesirable to change its appearance with captions or price tags. Dioramas in natural museums can also benefit from meta information that does not interfere with the artifacts. And SpecTrans allows us to support these complex scenarios. So here are 4 transparent materials that are virtually indistinguishable to human eye, but SpecTrans can classify them in real time. So we were inspired by a large body of work that focuses on interactions with transparent surfaces. We, however, wanted to expand this by enabling material classification in those scenarios. SpecTrans allows us to tag information to raw materials without any instrumentation to the environment, also without additional cost. So these are the 8 transparent materials that we use as an example and also in our evaluations. So how can we classify these types of transparent materials at high speed using an embedded device? So in SpecTrans, so we propose sparse high-speed sampling of the BRDF. So we will explain the technical details in the following slides. The bidirectional reflectance distribution function represents how the surface reflects light from certain incoming direction to certain outgoing direction. So when there is incoming light from one angle, there will be a distribution of reflected light, like this green lobe. So this is a 4D lookup table. It's a 2D for incoming angle and 2D for outgoing angle. A mass surface, for example, has a flat distribution of its reflected light intensity with its diffusive characteristics. On the other hand, a specular surface, like polished metal, has a peaky distribution for reflected light intensity pattern that is closer to ideal mirror. And these reflection functions can also differ based on the incidental light directions. This is in x-axis on this slide. So finally, the characteristics are all different for different light wavelengths. And here, our goal in this project is not the complete capture of the BRDF property of the materials, but sparse sampling of BRDF. So it's a small subset of the It's a small subset of the complete BRDF, but it provides enough information to classify different materials. So we can achieve this with a set of light sources to illuminate the surface under different angles and wavelengths. And high-speed image sensor can capture sparse representation of the BRDF at different exposures. The white one is the image sensor, and it's looking at the surface, and there's laser illumination and LED illuminations from different angles.
Next, I will talk further details of SpecTrans. We developed a custom PCB for SpecTrans to house an image sensor and multi-spectral, multi-directional illumination. Here, this is the front view of SpecTrans. Our setup consists of an optical mouse image sensor with 30 by 30 pixel resolution, a laser emitter, and 20 LEDs in 4 directions. Each position contains LEDs at different peak wavelengths of red, green, blue, and 2 infrared LEDs. The image sensor we used has an interesting feature. It can do some simple image processing on chip and extract 4 key features: average brightness, darkest pixels, brightest pixels, and pattern granularity of the surface. We took advantage of this function for classifying surfaces and successfully reduced the amount of data to be transferred from 900 bytes to 4 bytes. One of the contributions in SpecTrans is its use of various lighting conditions for classifying different materials. SpecTrans has 26 different lighting conditions, with LEDs in 5 different wavelengths and 4 locations. Here, we can see how SpecTrans captures these 4 surface features in those 26 lighting conditions under 4 fixed exposure periods. So this video is slow motion. It is 220 times slower than real one. Given the high speed of our sensor, SpecTrans can thus collect 416 samples and classify materials in just 170 milliseconds. Next, I will mention about the performance evaluation of our sensor. We evaluated how accurately we could classify materials. We computed the correct classification accuracy for these 8 transparent materials, and also air, as a baseline. If we only have single directional LED illumination, 2 IR LEDs and RGB LEDs from one direction, we get low classification accuracy of around 65%. However, by combining with multi-directional illumination, laser and 5 LEDs from each 4 directions and all 4 directions, like this, we can reach 99% classification accuracy. This means that the combination of laser and multi-directional and multi-spectral illumination is contributing to more accurate classifications. The unique characteristics of SpecTrans enable various applications. It both supports traditional material sensing, but also unique surfaces that are not possible with conventional sensors.
Transparent showcase is made of 6 different materials on each side. By placing a smartphone equipped with our sensor on one of the 6 sides of the cube and hitting a detect button on the screen, it triggers different annotations. This example shows a model of Wright Flyer in the showcase. By scanning the frontal face of the showcase, the screen displays the old footage of plane flying towards the user. When the user scans the right face of the showcase, where the propeller of the plane attracts more attention, an animation explaining how the engine and propeller work will be played. Finally, when the user scans the top of the showcase, a top view blueprint of the airplane appears on the screen. We can also use SpecTrans to bring interactivity for large transparent surfaces, such as windshields or shopping windows. Here, a glass wall has been enhanced with 3 transparent control surfaces that are made of different transparent materials. Each surface is associated with different controls: pan, rotate, and zoom. By embedding SpecTrans sensor in a smartphone, we can create a smart home button that changes behavior based on the user context. When a user is controlling a phone with bare hands, it shows a normal home screen and address book. However, when a user is wearing a glove, a set of large icons that are used more frequently will show up for easier navigation. All these user contexts are detected by the material sensor automatically. Another application is to enable faster switching of viewports in 3D CAD software. Each viewport subwindow is associated with an area on the mousepad. Similarly, we can use SpecTrans to control multiple virtual desktop windows. SpecTrans can also be used to enhance conventional interactive screens, like a tablet device. In this example, a salesperson is preparing a quotation in a business meeting. The salesperson can see both the cost and other information, such as how many stocks left in the warehouse. When the salesperson shows the quote to a customer, he removes the transparent cover of the tablet. As soon as the cover is removed, the costs will disappear, and the customer can only see the items and the total sum. Like this, we can add a transparent but physical layer to interactive screens.
In conclusion, in this presentation, we introduced a versatile surface classification technique based on multi-directional and multi-spectral capture of optical material properties. We described the design and implementation of sensor, and this enables real-time material classification on embedded microcontrollers. Also, we reported the results from classifying 9 transparent materials, including air. Finally, our evaluation shows a promising rate of 99.0%. Today, we present the SpecTrans sensing technology. We have also showed you a small set of applications, mostly in human-computer interaction domain. Our ultimate goal is to make the physical world more interactive, and we hope this project will help pushing toward this direction. Thank you for your listening.
Daniel Ashbrook from the Rochester Institute of Technology. One of the issues, of course, with a clear surface is that you don't have anything written on it. So I'm curious if you've thought about how to indicate to the user the possible function of each of these different kinds of surfaces.
Well, that depends on the context how this technology is going to use. Like in this, museum showcase example, the site, structure of the object itself has some information, and also in this presentation we focused on the transparent materials, but actually this technology is versatile for colored and textured surfaces as well.
Thank you.
I'm Seung-Chul from KAIST. I just have a question about the non-flat surface. We sometimes see some spear-shaped glasses or some things in museum. So how does it work for some curved surface or some other shape of surfaces?
Well, in this our particular configuration, we used kind of repurposed laser image sensor, and laser image sensor has neither lens in front of it, and the focal length is fixed. So in our case, I'm sorry. Okay, the short answer is you can use it with curved surface, but with our current setup, the distance between the sensor and surface needs to be fixed. I'm sorry, I'm answering your question.
Quite not sure, but okay.
Okay.
Thank you.
Yeah, yes, we can combine this technology with other sensing technology, and yeah, I want to emphasize that this SpecTrans is not going to kind of replace other 2D markers or fiduciary markers, but it works with them. So it's complementary technology. You can also combine multiple different transparent materials, then create kind of transparent markers as well.
This is amazing. We are talking about a sustainability session. This technology can be applied to automated recycling and a correct classification of reusable materials. It's very difficult to differentiate PVC, PET, something like that. So this is very valuable, I think. Thank you.
Yeah, thank you very much.